Okay, well, maybe we should just get started. We'll show up when it shows up. Okay, well, thanks for coming to the special bonus talk. So we'll have two short talks. Our first, it's our pleasure to have on Anh Tran from UIC. We'll be talking about the non-abelian Hodge correspondence for higher dimensional quasi-projective varieties.
Okay, thanks for the opportunity to talk here. My first part of the talk will be just introducing the non-abelian Hodge correspondence on the projective varieties. And it will be a preview for the introduction talks that will follow in subsequent weeks here, I guess. Okay, let me try to motivate the names. So one reason that you can call this the non-abelian Hodge correspondence is the reason that Hank mentioned yesterday. But you can see of it, you can view it as a way of generalizing the Hodge decomposition to non-abelian coefficients. But there's also a strong analogy with basically trying to bring in 3 points of view of studying algebraic varieties. So you have the topological point of view. So let's look at the classical Hodge decomposition on a projective variety X. You have the singular homology with C coefficients. And on the algebraic side, you have the algebraic de Rham complex, and you can take the hypercohomology of that. And by a theorem of Grothendieck, these are isomorphic. And lastly, on the differential geometric side, you have a decomposition of this into a direct sign. This is called the de Waal side because this is also called the de Waal homology. Okay, so what would be the analog in the non-abelian case? So here we will basically look at homology with coefficients in GLC instead. So what we will look at are these hom from pi1 x to GLN C. But I guess we don't want to look at all the representation like this. We want to quotient out by the conjugate action of GLN, maybe GLR. This is defined to be my Betti moduli space, and the points of this Betti moduli space parameterize semisimple representation of pi1.
Oops.
And the corresponding object over here are algebraic flat vector bundles. And I will look at this, the Rham moduli space, which will be my moduli space of polystable. All right. And let me maybe remind you of the definition of flat bundles on a projective X. So a flat connection V and nabla on X is just a vector bundle V, so locally free sheaf. Equipped with a C linear map, nabla, from V to V tensor with the cotangent bundle. X. Satisfying the product rule and having curvature 0. Okay. And on this double side, we have the moduli of Higgs bundles, polystable Higgs bundles. Oh, let me just mention that the polystable condition on the round side is very easy. It's just basically mean it's a direct sum of stable flat bundles, and a flat bundle is stable if there's no sub-flat bundles. On this double side, the polystable condition actually matters. It's 3-0 as well. And basically, the way to think about it is that one of the main point of stability is that you want to construct a moduli space of vector bundles. And so if you consider all the vector bundles, that is too big. So stability gives you like a notion of boundedness that allow you to construct an algebraic moduli space. And let me give the definition of Higgs bundle as well. So Higgs bundles is also a vector bundle E equipped with something, this Higgs field, which is now this is a OX linear map from E to E tensor if you make a one, such that the bracket of this Higgs field is 0. Equivalently, another way of thinking about this condition is that this Higgs field gives you an action of the symmetric power of the symmetric algebra, the tangent bundle of X on E. Right, and we have the following theorem. The first one is the Riemann-Hilbert correspondence. Which say that you have an equivalence of category between the category of representation of pi1, say rank R representations, and the category of, say, frame flat bundles of rank R on X. And the way this works is that you have given a representation of pi1, you can construct the following holomorphic vector bundles. So you go up to the universal cover of X. You take the trivial vector bundle rank R on the universal cover. And then you quotient out by the diagonal action of I1. So XV is identified with this. And the connection comes from the exterior derivative on this trivial vector bundle. So this is with D. And the nice thing about this Riemann-Hilbert correspondence is that if you restrict it to the polystable flat bundles, it actually gives you a complex analytic isomorphism between the Betty and the Ram moduli space. Okay. And I'm finally ready to state the non-abelian Hodge correspondence in this projective case. All right. There is an equivalence category between polystable flat bundles on X. And the polystable degree 0 Higgs bundles. And the way this works, I will mention briefly how this correspondence goes. Okay, so let's say that you are given a flat bundle. You're given a polystable flat bundles. Then there exists a unique, well, not unique, there exists a harmonic metric on V. So let's just forget about the harmonic part for a second. If you have a metric H on V, you can decompose this connection, nabla, into something that is unitary with respect to H, plus something else here. And then you can further take the type decomposition of these two operators. And the condition that the metric is harmonic is saying that this operator is integrable. So the correspondence here is you are given such a flat vector bundle, you map it to it's the same underlying smooth vector bundles, but now you equip it with this new complex, new holomorphic structure. And then the Higgs field is this theta. And once again, we get a statement on the moduli space as well. This correspondence actually gives you a real analytic one. It gives you a homeomorphism between the the round moduli space and the double moduli space. Questions so far about this?
Are you assuming projective everywhere or quasi-projective?
Projective everywhere for the moment. Yes. Let me give an example. Like the easiest example is rank 1 bundles on an elliptic curve. Okay, so the Betty moduli space here is just from z square to c star. And then you have to proportion out by the conjugate action of c star, but that's trivial. So you can forget about this. So this is just c star square. The double space is also easy. So we are on a curve. So this symmetric condition is automatic. So this double space is just a space of a degree 0 line bundle on E equipped with some Higgs field. And this is just Higgs naught of E. Direct product with H naught of E. The reason is because you can view this Higgs field as a map from as a global section, the homomorphism of E tensor with omega 1x. And if you have a line bundle, then the endomorphisms is just trivial. So the Higgs field is just the same as a global section of omega E. Okay. The round space. So you still need an underlying degree 0 bundles. But you know, if you fix an L, it's a big knot of E, then the space of flat connection on L forms like an affine space. Because let's say that you have two flat connection, nabla 1 and nabla 2. And you take the difference between the two of them, that give you an actual OX linear map, because the DF part cancel out. So this omega E here is just, it's trivial because we are on an elliptic curve. So if you want, this is an OE torsor over E. It's a non-trivial torsor. And you can already see most of the feature of this correspondence in this case, because these two are complex analytically isomorphic. But so this is just E plus C. But it's only real analytically isomorphic to this E plus C. Maybe let me mention I will move on to the quasi-projective case. But let me start with mentioning some issue. If you just try to put this whole formalism directly. On quasi-projective X, we can still talk about the moduli space of pi1 representation. That's still fine. We can also try to talk about the moduli space of all flat bundles on X, but this is already an issue. One example that we can look at is just X equal to A1. There, every line bundle on A1 is trivial. So a flat line bundles on A1 is the same as the trivial vector bundles, equipped with some flat connection. And by the same reasoning as above, every flat connection on this trivial bundle will look like D plus some global section of omega X. Okay, so the space of flat line bundles on X is isomorphic to this H naught of omega X. We are on A1, so this is trivial. So this is just O of A1. So this is isomorphic to CZ, the polynomial ring. And this space is infinite dimensional, so it's bad. And another thing is that for the Dubois space, this notion of stability actually matters. And it only really makes sense to talk about stability on a projective variety. So both of these issues lead to this notion of a log bounds. Okay. So definition. A log smooth variety for me will be a pair X bar and D, such that X bar is a smooth projective variety. And D is a simple normal crossing divisor inside of X bar. So log flat bundles for me would be a vector bundles V with some log connection, which in this case go from V to B tensor with omega 1 log D, such that it satisfies the product rule and it's also have zero curvature. And I have a very similar definition for the Higgs log Higgs bars. And now it's the same thing. I require this map to be OX bar linear. All right. This is still not nice enough yet. We also have a notion of a harmonic metric on these log Higgs bundle, but you know this solution to getting a harmonic metric is no longer unique anymore, unless you fix some condition. So the actual space that we will look at here is the following. So on the Betty side, we will look at all the representation with unipotent local monodromy. So let's start. And then on the RAM and the ball side, I will require the residue along this D to be nilpotent. Then we do have a nice non-abelian Hodge correspondence in this situation. So this is a result of Mochizuki and Chern, Brunebarbe and Tsimerman. Which basically say that you have a homeomorphism between this double space and this derived space. Maybe plus epsilon. So basically, Mochizuki proved that there's an equivalence of categories between these two. So there is, if you want, he gave a set theoretic bijection between these two sets. And then this recent paper proved that you have a homeomorphism in the case where X bar is a curve. So this is a homeomorphism. This is true when and they also prove that this is a continuous bijection when X bar is a higher dimensional variety. Okay, so let me outline the strategy for moving from the curve case to the more general case, and then I will tell you how to strengthen that into a homeomorphism. So the idea is that there exists a Lefschetz curve C psi x such that you have injection of fundamental group. Okay. And that would give you, we have a version of the Riemann-Hilbert correspondence in this quasi-projective case as well. And that will give you a closed immersion for the RAM space. So we have this diagram. Let me drop some of the adjective. Okay, so we know that this is a homeomorphism. And we know that this is a closed immersion. This is an algebraic map. It's a continuous bijection. And this is also a bijection.
Injection.
Yes, this is a continuous injection. So the argument is that if all four of these are true, then this map here has to be a continuous bijection. And the improvement is that you can actually show that this map is proper. So it's a closed injection. And that's enough to say that this has to be a homeomorphism. And I think I'm out of time.
Maybe we have time for a quick question.
So you can prove it's homeomorphism now? Is that
Yes.
the improvement? Okay,
Yes.
great. And the map is proper. You have only the monodromy assumption on C. You don't need to know that it passes through like every component of the boundary or anything like that.
I don't think so.
Okay.
Yes.
Any other questions? Maybe I have a question, which is, can you in 30 seconds explain the proof?
Sure, maybe. I can draw a diagram. Let's see. So the way to prove that this is a proper map is by using this proper valuative criterion for properness. So let's say that you have some dVr, R, and some width fraction field K. You have the following diagram. And it will be proper if I can show that there's a lift. And I can extend this diagram by using something called a Hitchin map to some base here. So the idea is that I can pick a sufficiently ample C such that this map is an injection. So if this map is an injection, then I have a lift here. And then this Hitchin map is proper. So that will give me a lift over here. And it's easy to check that the diagram has to commute.
But you prove it's proper.
Yes, but it's a follow from something.
All right, great. Thanks. All right.